trees in it, so I'm going to start with the wood and move back to the trees. And so basically, let me start with this. There are two ways that H0 can vary observationally. Now, I've highlighted observationally here because you're a cosmologist and you do observations, you fit data. So with redshift, you could imagine H0 varying with redshift, right, on the sky, okay? And you can also imagine it varying with direction on the sky. Now I'm going to talk about what happens when H0 varies with redshift in a model. So what it means is the model is breaking down. So it's a signature of the model breakdown. Now the other thing is that you can go after FLRW if you want by looking at variations of H0 on the sky. Now there's a very interesting systematic, or whatever it is, in Planck data. It's pointed out recently by two groups, people who are presumably in the Planck collaboration at some point, or are collaborators, where they looked at smaller sections of the CMB, and then the paper I like is the one by Eoin and Chu, because they basically, they mask half the CMB, right? So they're splitting the sky, and then they basically rotate which half of the CMB they're masking, and they do it on 48 directions on the sky, and roughly what they find is there's a particular axis along which there's a particularly large variation in H0, and it's more or less 6 kilometers per second per megaparsec. But what's the interesting coincidence here is that aligns with a well-known CMB anomaly, which is the hemispherical power asymmetry. That was in WMAP data, and it's also in Planck data. So it's sort of compelling that that thing is there, and it's a place to start thinking about FLRW. Okay, so I'm going to do some maths. This is FLRW. These are the equations you solve. These are the most fundamental equations in all of cosmology, right? If you do frequent universes. We have a pressure, we have a rho, a density. They're functions. They're either functions of t or functions of z, whichever you want to look at it. And we need to specify this guy to solve those equations. If you don't specify what the W effect of z is, you can't solve those equations. So this is a theoretical input at the beginning. You have to pick that. Now once you pick this guy, which is essentially a model, then you solve and you get h of z. So that's just a mathematical statement. I have one function, W factor of z. I have my integration constant. H0 comes because I solved the first order differential equation. And then h of z is the output. But as cosmologists, what you're actually doing, you're going off and you're going to confront this h of z to data. So you can read, like Alberto gave a talk. Alberto was basically reconstructing h of z directly from data. That's what you do when you do Gaussian processes or these reconstructions. And so in some sense, what you can do, you can sort of think of this as basically, I had two functions. One I put in by hand, it was a theoretical guess. And the other one is this a priori unknown function, h of z, the Hubble parameter, which we're going to extract from data. We're going to extract it directly from observations. And if they don't, if they don't have the same z dependence, then you have a very sharp prediction from here. The very sharp prediction is that basically what should be an integration constant, it picks up z dependence. So that's the basic simple idea here. If you've got a mismatch between what you expect, the Hubble parameter you extract from data, and then the assumption you made, the thing you put in at the beginning, the physics prior or whatever, then this guy you expect it to run. So mathematically, H0 has to be a constant, but observationally it need not be, and we need to check that. So this is just a consistency check of any model, right? That's what we're doing. Now, we have lots of discussions. This is the Tacoma Narrows Bridge. It fell down, right? And if a bridge falls down, you should have a look at the autopsy. You should basically go and examine it and sort of see, where did I go wrong? What happened? The other thing is to go and build new bridges, right? So those are your two approaches here. And the whole debate we're having on Lambda CDM is basically, is it systematics or is it new missing physics? But that's exactly the same debate as saying, is this systematics or is the redshift evolution of integration constants or constants in my Lambda CDM cosmology? So this is just essentially a definition I'm going to use of basically what model breakdown means. Now, in physics there's lots of good models. Like one of them is radioactivity. You can teach it to your students, your first years, go into the lab. You take something that's radioactive that has a short half-life. You can come in, you do the experiments. This week, you go in next week, you look at the activity again, you record that, you essentially fix these two guys, A0 and Lambda, and then you've got predictions that you can go forward in time. Next 6 months you can go back into the lab and you can sort of check all of those things. We are really only getting to the stage now in cosmology where basically we had predictions from the CMB, we have predictions from Planck or WMAP, and now we can go after them and we can test them in the late universe, right? That's where cosmology is at the moment. So this is a very natural part of basically forming a good physical model, right? But you need to have time-separated data. Like, you know, to test radioactivity, to test this formula, you're going to have to come back into the lab. It's very controlled, but you're going to have to come back at regular times, collect data. And the same thing should be true in cosmology as well. So what I'm going to advocate is basically, you know, redshift is time, we need to bin data by redshift, and we need to check that the cosmological parameters are not involved. That's the basic idea. And just to point out, Lambda CDM is a great model, right? It's simple, it's predictive, right? Which makes it very strong. The predictions may not hold up, but that's fine, this is all physics. Until relatively recently, you know, CMB, BAO, and supernovae, they all agreed on basically matter density, which is quite an achievement, and it makes it very robust. No matter what data set you have, you always get something that's very close to 0.3. Okay, so what I'm going to be doing is I'm going to be doing this in a subsector of the model. I'm going to simplify Lambda CDM as much as possible by just decoupling the radiation sector. So there's no CMB for me. I'm just doing late universe. It's completely trivial. I've got a two-parameter model. It's background. Now, the one thing about this is that with this simple model, I know cosmological data may not be the best, but basically you can go all the way from z equals 0 to, well, okay, let me put it in gigayears. You can go back about 13 gigayears. You go to z equals 30, you can go beyond, and this, we still expect this to be a good approximation of the background level. So that's the claim, right? Now, if that's true, that's an absolutely remarkable model. Or it's just too good to be true. Okay? And the other thing here is that in any observable, if you have constraints like observational Hubble data, or angular diameter distances, or luminosity distances, actually, if you just use those constraints on their own and never combine them, what you're actually doing is you're using data between z equals 0 and z equals 1 to basically fix the Lambda CDM cosmology. Because you only have two parameters. You have H0 and omega m. Now what I can do is I can bring my H0 inside and combine that into a parameter that's essentially sensitive to the dark energy density. And the only other parameter left in the game is the guy who's sensitive to matter density. So you essentially only have two parameters. And what most cosmologists, when you talk to them, what they say is basically, you know, we need to basically combine low redshift data and high redshift data to break the degeneracies, fix both those two parameters, but you already do that by z equals 1. So what is the data beyond z equals 1 giving you? What it's giving you is greater precision on data you've already fixed between z equals 0 and z equals 1. Right? So you're essentially modeling the universe, or claiming to model the universe, all the way up through 13 gigayears, maybe up to wherever radiation becomes relevant, with data that's basically only there between z equals 0 and z equals 1. So it's basically about, I don't know, it's 5 or 6 gigayears or whatever. But you know, beyond that, I don't think any of the data is particularly relevant. It improves your precision. I think this is a problem. It's a conceptual problem, right? That high redshift data is essentially just a spectator of the way we do it. Now, this need not be the case. What I'm going to show you here is basically, these are mocks of DESI forecast data. On the left-hand side, I basically have H of Z. One of them is D. Actually, it's not even clear to me which one is which at this stage. But one of them is H of Z, one of them is DA of Z. Right? So basically, I'm just performing like a couple of thousand mocks, realizations of DESI forecast data. I put them in 4 bins, they're redshift bins. Low redshift 1, next one up, between 1.5 and 2.3 and 2.3 and 3.56 or whatever it is, 5.5. Now what you'll notice is that it's maybe difficult to see here, but at low redshift everything's beautiful and Gaussian, right? So basically I'm breaking the degeneracy between those two parameters nicely in a H of Z constraint. Also in a DA of Z constraint, I'm also getting a nice breaking of that degeneracy. But as I go up in higher enrichment, and I should stress these are basically just best fits. They're best fits to the parameters. There's no errors. I'm basically, you know, 10,000 different realizations of the data and just tracking best fits. So it gives me a distribution of best fits. You find non-Gaussian tails. This is just a mathematical fact about the Lambda CDM model. There's nothing mysterious going on.
Is it a realization of the Lambda CDM model or of the data themselves?
It did 10,000 realizations of the data, and then I fit back the Lambda CDM model. But everything here is consistent with Planck, statistically consistent with Planck. The one thing to bear in mind here is, if I just had a high redshift bin, you can really just keep going up in omega m values, right? There's nothing to stop you getting into some regime. Alberto just gave a talk about negative dark energy densities. There's nothing for you that stops you basically getting best fits that would be in that regime. So if you bin your data by redshift, once you've sort of decoupled the low redshift part and you just have the high redshift data, you can easily get negative dark energy densities. Now the exception to that is in my mocks, if I combine H of Z with dA of Z, what I happen is, no matter whatever redshift I'm in, I always get back my input parameters. And this is really nice because what it shows you that, even if I produce mocks that are, you're in the matter-dominated regime, dark energy, you've already gone well beyond dark energy, but you can reconstruct it. It has a knowledge of that. And the reason it has a knowledge of this is because this is an integral. It's 1 over H of Z. And it's easier for this integral basically to make adjustments in the dark energy density because that's the relevant parameter. You can think of this as a weighted sum. And as I go up in Z, H of Z is an increasing function. So basically this is a weighted sum that's essentially biased towards low redshift data. Okay, so this is why this degeneracy works, right? Basically, you don't need low redshift data. This is an idea that cosmologists have, that I need low redshift data to break their degeneracies. That is only true when you do not have H of Z and dA of Z constraints. When you combine these guys, you can break the degeneracies at any Z, if you have the data to do it. So this is actually what interests me. And what motivated me originally was the strong lensing time delay and their constraints on H0. So this is a descending trend across the lenses. It could be a systematic. Last time I gave a talk, I think George was saying this is a systematic. It could easily be a systematic. Now what interests me is that basically the strong lensing time delay people are being honest. They're doing the same thing. If they do the analysis, if they follow the same pipeline, there really is no reason for them to get this. Unless your cosmological model is breaking down. Okay, that's the basic idea. And on the flip side, we had a talk yesterday on quasars, right? Now, what the speaker told us is basically at high Z there's an anomaly. Basically, nothing happens true to supernovae, but beyond that, we find some discrepancy with Planck. Now, we did some work with Salvatore, who's here, and Maria, who's here, and there's some fine print that I probably need to discuss, but the fine print is more or less that, when you use quasars for cosmology, if you actually want to do cosmology, you're going to have to take that luminosity relation at face value. The other way to do this is basically you put the cosmology in by hand and then you study that luminosity relation. Okay? Anyway, so what really surprised me was that if you take the quasar data, and our speaker yesterday didn't mention this, and you restrict it to the same redshift range as supernovae, you find a distribution that's essentially peaked where it should be. It's at the Planck value. So even though the quasar data below Z equals 0.7 or 0.8, I think in the paper it's 0.7, people say don't use the data below 0.7 for cosmology. You can get a Planck value. So basically where supernovae and quasar actually overlap in the same redshift range, they agree on Planck. But then you find an increasing trend in omega M as the effective redshift goes up. And you've got to bear in mind that the quasar sample itself is a fundamentally high Z observable. Its effective redshift is 1. Effective redshift for a supernovae sample is 0.3. So everything that you understand about Lambda CDM cosmology is biased by an observable that's a low Z observable. That's why quasars are so challenging. Quasars may just be, they may not be standardizable. We heard yesterday that type 1a supernovae are not standard handles. They're standardizable. You have to work hard to standardize them, right? And the same is true of quasars, right? It's not even clear if anyway, so basically the point here is any observable in cosmology, they're systematic, so you need to be careful. So you should only trust observations in multiple observables. Dark energy I trust because it's CME, BAO, and supernovae. If it was just supernovae, nobody would give a Nobel Prize for that. So you basically need to have this. I'm going to tell you about some now follow-up work in Pantheon Plus. Leandros was interested in one end of Pantheon Plus. I'm interested in the other end of Pantheon Plus, the high Z part of it. This just shows you that if you actually calibrate the Pantheon Plus sample, like with shoes, that there is a 3.7 sigma discrepancy with Planck. This is not so surprising. H0, is discrepant anyway. Just what interests me is it's now a discrepancy in that particular parameter which controls the higher redshift part of the Hubble parameter. Okay, I don't know if there's anything else to take from this. Now, what this is basically some stuff that's not on the internet. It's basically, it's a split of the Pantheon plus sample, basically where we split it by redshifts, and we have a low redshift sample and a high redshift sample. And basically, as we split it, these are the number of supernovae at low redshift, number of supernovae at high redshift. As we get to the high redshift, you're into small numbers. Below 0.7, it's 75 supernovae, 30, 27. I mean, still, the sample, you know, it's meant to go all the way to 2.26 or whatever it is. But there's only like 25 supernovae. It's very sparse. Now, what we're doing, Janus told you a little bit about how the Pantheon Plus data set operates. What we're doing is basically we're moving our 77 supernovae in Cepheid hosts. We're basically, what I'm doing is, sorry, let me say it this way. I have a covariance matrix. It's 100, like 1,701 times 1,701, and what I'm doing is cutting out that block diagonal, which is basically, it's the connection between the supernovae and Cepheid hosts and the rest of the supernovae. So I basically split it in block diagonals, right? So it means that my Cepheids, or my supernovae and Cepheids hosts, they're only used as calibrators. They only fix M, and they're essentially cut off. And the rest of the supernovae are then, once M is fixed here, then I can determine H0 and omega M over there. So that's the basic idea. So let me sort of point out what the trend is. The trend is basically H0 is more or less what it should be. Maybe it goes up a bit here, but then you find a descending trend in best fit values. So there's no errors here. And then you find, an increase in omega M, and it goes to some crazy values because I took my prior to be omega M equals, the bound could be 5. But you find an improvement in chi-squared by just splitting your sample, right? Now then you can go and do, this is just a plot to say, like, okay, this is a small sample of 25 supernovae, beyond z equals 1. But no matter where I start my extremization procedure, like, you shouldn't question best fits, right? In 25 data points with, 2 parameters, but basically, you could question them. But, depending on where you start in parameter space, you more or less get the same numbers, right? Now, the problem here is, like, as a particle physicist, I would just look at that and sort of say, okay, I'm in an unphysical regime of parameter space. I'm somewhere in the parameter space I shouldn't be, and why am I there? That's something in my data that's bringing me there. But as a cosmologist, you may say, well, that's my best fit. Now, as long as my errors are large enough, and I get back to the physical regime, then I'm okay with that. This is a slight cultural difference, right? But yeah, I mean, as I showed you at the beginning, once you get to high Z stuff, your distributions are completely skewed. Estimating errors are very, very tricky. That's why I'm not telling you what the errors are here. I've just provided you an improvement in chi-squared across the sample. And you could go to Fisher matrix. I assume you're using a Fisher matrix, right? So basically that gives you Gaussian errors. And MC is prone to degeneracy. So this is basically, if you take that upper part, this here is the lower part of the sample, right? So it's below z equals 1. This is the upper part. And basically, the whole problem with this MTMC thing is, like, basically, as we increase our bound on omega n, this peak is sort of robust, but then the distribution falls off very gradually this way. And what that's happening is actually, basically, you're extending into the upper left corner here, and that basically shifts the H0 to lower values. So it's not clear what I can take away from this MTMC analysis. I could basically impose a bound here at omega m equals 1. I could restrict it to the physical regime, but then the best fit is cut out. That worries me. Okay, you can certainly do that, right? You can impose priors, right? I want to be in the physical regime. Anyway, if you look at the difference in AIC, then basically, if we've got to, let me flick back a bit. The numbers here, that's -7. So you can basically absorb, depending on how you want to look at this, if you want to take D to be an extra 3 parameters. I know the AIC is a very simple thing, so you may want to question that. But there's definitely an improvement in chi-squared enough to basically absorb those 3 parameters, which would be a z-split, an extra value of omega m, and an extra value of H0. Now H0 and omega m are integration constants. Mathematically, they must be constants. Data says they like them to move, so you're in trouble, right? That's a contradiction. And then we also did some mock analysis, right? So I can't tell you what the significance is. I haven't been able to estimate errors, but what I can do is I can basically, whatever redshift range I'm interested in, I can produce mocks that assume there's no evolution through the sample in the same redshift range. And if you do that, here I'm just using sums. What these sums are, I'm choosing a range of different z's for my z-splits. Now these sums will basically be peaked. You know, this is the these are the values, best fit values for the full sample. They're very reasonable. Those are the errors. I'm basically generating large configurations that are consistent with these, an array of these three numbers that are consistent with these errors, normal distributions, yada, yada. And then basically you generate, for each one of these you produce a data set, a mock, and then you basically evaluate these sums on those mocks. And what you find is your real data set here, and of course this is peaked on 0. Same, in the mocks typically there is no evolution. On average there's none, right? And this is basically places this, I think, at I don't know if it's peak. It's about 8% chance or something of that happening. So we saw 7% and 2% here, right here. And this one here is basically a little bit more specific. I mean, this I regard as this is not an a posteriori statistic. It's very mild, right? I'm not putting in the redshift split. Here I am putting in some data, so I'm basically asking what is the probability of getting negative dark energy density in the ranges that I see it, and what is the chances of getting negative dark energies this large? Now let me skip to my conclusions, so I can just pull what those are. So yeah, the probability of, basically for the mocks, it's about a 10% chance, okay, of getting a omega n greater than 1 in each of the bins that I do see it, or each of the ranges I do see it. For the sums, it's about the same number, and this is much smaller. Like to get a suitably large, to get as large negative large omega n values as I do get, I mean, the probability of that is about 2.5% or something. So it's roughly 1 chance in 40. This arising statistically. I mean, and this is only one data set. I haven't shown you the quasar data set, and this also happens in observational Hubble data as well. And there's nothing to preclude it happening. Right, so on that, it's really important to look for this, right? Evolution in these guys. Okay, on that, I'm done.
Any questions, comments?
Yeah, right.
Why do you split the sample into 2 block diagonals? Because this way, others will complain to you and will tell you, you are missing correlations.
Right, so basically, I've done this 2 ways. I didn't show you, but if you restore the covariance matrix, the problem is that, those calibrators, I want to use the same calibrators for the low redshift and the high redshift sample. Okay, so that's why I isolate those, just to set the scale. Now, I'm using the same 77 Cepheids all the time, supernova and Cepheid flows all the time. I could have replaced that with a Gaussian prior, which would basically just be this number here, right? So it would be, this is the same one as yours. My m is minus 19.25 plus or minus 0.03. So I could just use Gaussian prior. But if I do restore the covariance matrix, and I haven't showed the results here, but this trend is robust.
So you fit separately the Cepheid part? You fit separately the Cepheid part?
No, I've done this analysis where I split everything, and then I just focused on the high Z part of it with the full covariance matrix as much as possible, with the off-diagonal terms.
After fitting the low.
The thing is, I have to do, basically my Cepheids have to go, the Cepheids have to go somewhere.
Why not keep them interacting in the same sample?
Because then I worry that basically I have the overlapping data, right? Let's discuss it in a bit. You can tell me, right? There may be ways to improve this analysis, right?
I think about redshift build, and automatically, I think about different surveys, yes, which are, implemented by Eoin Plus. And Eoin Plus is a hybrid data set.
Right.
You have PS1 and PS2.
Yes.
Would it make sense actually to look at the samples separately? Or
The covariance matrix is included here, and I think I agree with things in the literature that it's sort of overestimated, right? So you've got a large covariance matrix that sort of covers over these surveys, right? I think we all agree. You agree, I agree. Armin Shafton and Brian Keeley, they agree as well, right? So that's 3 data points. Okay.
Yeah, Manus.
So in your conclusion, you said that the information criteria
Oh, sorry.
preference over Lambda CDM.
Oh, this is very simple though, right? I mean,
So with
just on the AIC.
a transition of what and where and when?
Transition is, so basically anywhere in this table where I basically hit, I mean, so that's an improvement in chi-squared from the low z part of it, and that's an improvement in the chi-squared from the upper z part of it. So at z equals 1, you know, I can basically refit both subsamples and get an improvement.
I mean, is exactly one, or it can
You
be.
do well, look at the data points here. This is 27, 25, 20. I mean, it is not much we have to work with. I mean, Pantheon Plus and Pantheon are sold to you as data sets that basically go from 0 to 2.26. And the reality is there's very few data points beyond z equals 1, right? And just to point in, the assumption when you fit data sets is that there's no evolution. What this test is actually doing is testing that assumption.
Anything else? Yeah?
Just a comment that when we use the AAC criterion, we should also pay attention that in principle, this is valid for Gaussianity assumption.
Right. I agree.
Although, you know, in statistics, it would be very, very complicated to add another test. So this AAC is sort of happening. So if we are okay with the AAC, then we know that we'll be okay also with more complicated statistical tests. But also in my previous talk, I didn't mention that we would need to even more.
Right. I would say that the equations have much better statistics at high Z than this, and you see the same thing, right?
Yeah.
I mean, it's.
Okay, so maybe we can try going again.